Hi. Next operation that we're going to cover over here is matrix multiplication. Okay, and that's just before we need to start with conformability conditions. In case of matrix multiplication, they are very specific. Okay, so look. If we have two matrices, and this is n by n, and the second is L by K. Now look, we will be able to multiply those matrices if and only if number of columns in the leading matrix, matrix A, is exactly the same as the number of rows in the second lagging matrix. So those two need to be equal. So look, the conformability conditions here are very simple. Number of columns in the first matrix must be exactly the same as number of rows in the second matrix. And look, as a result, we will obtain some matrix C, and we can already read the dimension of this matrix, because you can think of it as those two cancel each other out, and what we get is M by K. And this is basically the conformability conditions. If we want to multiply two matrices by each other, we need to make sure that those two dimensions that lay the closest to each other are simply the same. Okay, and the entire process of matrix multiplication, I'm gonna describe you using an example. Okay, so let's just say we've got two matrices, A, size 1 by 2, and it's A11, A12. And we want to multiply this by the second matrix, B, B11, B21, B12, B13, B, oh, this one is 1, 2, 3, B22, B3, B2, 3. Okay, and look, I'm going to do it very slow. Now, look, the entire process of matrix multiplication relies on a very simple principle. But okay, look, first we know that we can multiply those matrices because the number of columns in matrix A is 2, and it is the same as the matrix of rows in numbers B. Number of rows in matrix B. Okay, let me just put them together here. A11, A12, B11, B12. And look, here this matrix has some additional elements, right? But for now, it's not important to us. Okay, what we know right away is that the new matrix, matrix A times B, will have dimension 1 by 3, right? So, how do we multiply matrices? Look, the entire idea of matrix multiplication relies on the fact that we always multiply a full row from the first matrix by a full column from the second matrix. And look, it makes perfect sense. The number of columns here is the same as number of rows. So multiplication like that makes perfect sense, right? Okay, so how do we do it? Look, we go step by step. So first, I take first element from the first row, and I multiply multiply it by the first element from the first column of the second matrix. And I get A, 1, 1, B, 1, 1. Then I add, and I multiply second element from the first row, the second element from the second element from this row and second element from this column, right? So column by row. Okay, so we've got A, 1, 2, B, 1, 2. And of course here we will have two more elements, but to those we'll get back later. Okay, now that we've got the first element, if we calculate all this, we will get our first element. But now let's say we're going to do it in steps. So now we can forget about these elements. We can, B to 1. I'm sorry, I'm making this video very late. So B to 1. Okay, now we will have elements B 1, 2 and B 2, 2. And some elements over here, right? Now, again we proceed with in exactly the same fashion. So first element from here. So first element, so from first row, remember, row times column. So this times this, and over here we will have A 1, 1 times B 1, 2, and we add to it, if I multiply it, take the second element, multiply the second element, and over here I get A 1, 2, B 2, 2. Okay, and of course now we need to finish, so we need to use the third row. A 1, 1, A 2. Now we are not interested in this and this and this and this. Interested in B1, 3, B2, 3. Now, first two places are irrelevant. And now, again, first element from here, A 1, 1, B 1, 3. And this plus A 1, 2 times B 2, 3. Now, if we would calculate all these values, we would get the outcome of matrix multiplication. Okay, let's try another example. Okay, so now we need to multiply, again, two matrices, matrix A and matrix B. Okay. So matrix A is 1, 2, 4, 3, 8, 0. And this matrix is 5. So this matrix is 3 by 2. This matrix is 2 by 1. Can we multiply them? Of course. Those two dimensions are the same. Okay, and now how do we proceed? Look, I'm going to be doing it for as long as I can with colors, but then everything probably won't be so visible. So, look, I always need to multiply entire row from the, okay, maybe let's do colors now. Entire row from the first matrix by entire column from the second matrix. But because the second matrix is a vector, well then we just multiply each row by the full vector. So we get that this is 1 times 5 plus 3 times 9, right? Then, and look, this element is, okay, one more thing, okay. This matrix that we've got over here will have a size, will have dimension 3 by 1, right? So look, actually, each step of the multiplication is also related to the location over here. Look, this first element we want to calculate over here. This element, this new matrix has 3 rows, 1 column. We want to have an element that lies in the first row and the first column. What do? We take the first column, the first row, and multiply it by, from the first matrix, and multiply it by first column from the second matrix. So we get 1 times 5 plus 3 times 9. Then this element lies in the second row, first column, so we use second row, first column. This is 2 times 5 plus 8 times 9. Now, this element lies in the third row, first column, we use third row, first column. 4 times 5 plus 0 times 9. So, we get that this is 5 plus 27, so we have 32. Here we have 72 plus 10, it's 82, and 20. Okay, so as you see, it wasn't that bad. And I think at this moment, we are getting a hang of it. Okay, so, look, in the next example, let's get even a bigger, even a bigger matrix. Bigger matrices. So we've got now matrix 3, 1, 4, negative 1, 0, 0, 2, 3, 2, and matrix 0, negative 1, 0, negative 1 over 5, 1 over 5, 2 over 5, 3 over 10, 7 over 10, and negative 1 over 10. Okay, so now can we multiply them? Well, of course, those are square matrices of the same dimensions. We definitely can multiply. Okay, so how do we proceed? Look, let's go element by element. Look, this here, first we need to look at this element of a new matrix that will also be of the dimension 3 by 3. So we want an element that lies in the first row, first column. So I'm going to use first row, first column, right? This element lies in the first row, first column. I'm using first row, first column. So I get that this is 3 times 0 plus negative 1 times negative 1 plus 2 times 0. Okay, now I want to know what is, now I want to get this element. This element lies in the new matrix, in the second row, first column. So now I'm going to use second row, first column. So I've got 1 times 0 plus 0 times negative 1 plus 3 times 0. Then I'm going to find the last element, the element that should be over here. So this element lies in the third row, first column. So I'm using third row, first column. This is 4 times 0 plus 0 times negative 1 plus 2 times 0. Okay, now So now I need to take as a point of reference second column of this matrix. And again, this element here lies in the first row, second column. I multiply first row by second column. So I get here that this is 3 times negative 1 over 5 plus negative 1 times 1 over 5 and plus 2 times 2 over 5. Then next element, second row, second column. I use second row, second column. Okay, so this is 1 times negative 1 over 5 plus 0 times 1 over 5 plus 3 times 2 over 5. Okay, and finally, this element lies in the third row and second column. So 4 times negative 1 over 5 plus 0 times 1 over 5 and 2 times 2 over 5. Okay, unfortunately, I'm not able to finish everything here. So let's just say that I'm gonna finish the last third column that should be here. I'm gonna finish it over here. So look, now we want an element that lies in the third, lies in the first row, third column. So I use first row, third column. Okay, so I get that this is 3 times 3 over 10 plus negative 1 times 7 over 10 plus 2 times negative 1 over 10. Then, second row, third column. So I get that this is 1 times 3 over 10 plus 0 times 7 over 10 plus negative plus 3 times negative 1 over 10. And finally, this times this, this times this, and this times this. So we get that this is 4 times 3 over 10 plus 0 times 7 over 10 and plus negative plus 2 times negative 1 over 10. Okay, so now we've calculated everything. What are we going to get? Okay, 0, 1, 0. So we'll have 1 over here. 0, 0, 0. 0, 0, 0. Negative 3 over 5. 4 over 5. Negative 1 over 5. 0. Negative 1 over 5, 0, 6 over 5, 1. 0, negative 4 over 5, 4 over 5, 0. Then, from here, 9 over 10, negative 7 over 10, negative 2 over 10, 0. 3 over 10, 0, negative 3 over 10, 0. And 12 over 10, 0, negative 2 over 10, 1. And look, basically, this is how we multiply matrices. Remember, the key to matrix multiplication is in multiplying each row from the first matrix by each column of the second matrix. Now, what we got here is a special case of matrix. This is the matrix that is extremely important in matrix algebra, and we call it identity matrix. Okay, now let's now we actually learned quite a lot. We know how to by a scalar. But can we relate it to the problem? And can we actually relate it to the problem of solving systems of simultaneous equations? As it turns out, we can. Look, let's just say that we have a system of simultaneous. Okay, let's just say that we've got a matrix like this. This matrix goes like 6, 1, 4, 3, 4, negative 1, 1, negative 2, 5. And we need to multiply it by x1, x2, and x3. Look, this looks familiar, right? When we took the system of simultaneous equations into matrix notation, this is what we had, right? Matrix of coefficient and vector of endogenous variables. What happens if I'm going to multiply them? Well, can 3 by 3? This is 3 by 1. Well, I definitely can. So why not, right? Let me multiply this now, and we've got 6 times x1 plus 3 times x2 plus x3, right? Now, 1 times x1 plus 4x2 minus 2x3. Then I got 4x1 minus x2 plus 5x3, right? All I did is I multiplied each row by the full column, because this is the only thing I could do. And look, of course I get a vector 3 by 1. And now look, let's just say that I would equalize this vector with some numbers. Second. Now, it already looks very similar to something, but not quite yet. Okay, so let me get rid of this part. Still bad, right? How about let's get rid of those matrices? No, I think now it's missing. What do we have? Look, this is the system of 3 simultaneous equations with 3 variables, not written in the matrix form, right? Look, but as it turns out, if I'm going to take, I can rewrite this system into the matrix notation. And this is exactly the same thing, right? Because look, when I multiply matrices, I get this. And also, I will get out of this is 3 by 3. This is 3 by 1. And this is 3 by 1. Look, out of this, I'm going to get a vector 3 by 1, which means that this must be equal to this. Because matrices are equal if all the corresponding elements are the same, right? So this must be equal to this. This must be equal to this. This must be equal to this. It's exactly the same thing. It's just written differently. Okay, so actually this allows us to draw a more general conclusion. Look, every system of simultaneous equations could be written in this form, where this A is our matrix of coefficients, this X is vector of constant endogenous variables, and D is a vector of constant terms. Now, so look, we can clearly see from that if we would be able to divide both sides of this equation by A, somehow, we would get x, right? So, if I want to solve, okay, this means equilibrium or solution, I will explain asterisk later, sorry, force of habit. Now, so the next thing we should do is to learn division, right? If I know how to divide, I will be able to obtain the solutions. But unfortunately, there is no such thing as division in matrix algebra. Well, there is something like division, but it's not exactly division. We will learn that actually we can obtain inverted matrix A, and by multiplication we will get identity matrix. But enough. For now, just remember that there's no division, but we can somehow multiply by reciprocal. Right? We will deal with this a little bit later once we know a little bit more about matrix algebra. Okay, so let's try. Okay, so before, so look, basically this far, I showed you how matrix multiplication is done. So I hope even from these simple 3 exercises, you can figure out how to multiply any 2 matrices. It would be good if we could write this down formally. And we will. But let's get back for a second to the sum symbol. Okay? So we remember this. When we have xi equals to 1, this tells us to add all elements. x1, x2, plus until element xn. Right? Now, we also learned that if I, for example, add a number over here, a constant a, what will I have? A x1 plus a x2 plus a x3 plus a xn, right? So we can take, for example, a out. And this is equal to what? Well, this is going to be equal to that. So we get that we can take this constant out of the sum symbol, right? And this is a very important property. And today what I wanted to do with you is to try a couple of properties like that with matrices. So maybe we can better understand how matrix multiplication is done when we see the formula that allows us to actually do it. Okay, so now we've got what else we would like to do. Okay, imagine a case like that. So if I have I0 here and I x I, how should I rewrite that? Look, even though we have 2 different i's, we still proceed in the same way. We will have that this is a0 times x to the power of 0, or simply a0, plus a1 x to the power of 1, plus a2 x to the power of 2, plus a3 x to the power of 3, plus until an x to the power of n. Wait. Haven't we seen this somewhere? No. Well, I can get rid of this one, right? Because x to the power of 1 is 1. x to the power of 0 is 0. Well, this is nothing more than the formula for polynomial function. So look how useful the sum symbol is. We could, instead of writing such a long formula for a polynomial function, we could have just used this. And it means exactly the same thing. And of course, if I'm only interested in polynomial of order 3, it's great, right? Okay. Let's do just maybe one more example with the sum symbol. I think we will be ready to use the sum symbol. In order to define multiplication. Okay, let's just say that now we have n I equals to 1 a x I plus b y I. Okay, let me rewrite this a little bit. I get that this is a x1 plus a x2 plus until a xn plus b y1 plus b y2. Actually, no, I'm cheating. I'm cheating here. This should be done in the second step. Look, first it should be done like that. Right? A x2 plus b y2 plus until a xn plus b yn. Right now, as I already showed you, what we can do is we can organize those expressions in a different order. Let's put everything with x together, let's put everything with y together. So we've got that this is a x1 plus a x2 plus a xn plus b y1 plus b y2 plus until b yn. We can notice that I can take a out of this, b out of this. So this is a x1 plus x2 plus until xn, then plus b y1 plus y2 plus until yn. How can I write this differently? Well, simply as a xi and I equals 1 plus b and I equals 1 y. Okay, and of course, in exercises that I've given you, you will have way more chances to prove some, to find some shortcuts with the sum symbol. But I think with what we've done at this moment, we will be ready to formalize multiplication of matrices. Okay, so first, let's just say that we have matrix A with the dimension m by, let's say z, right? And I need to multiply it by matrix B with dimension z by n. And of course, we know that we can multiply those matrices because the number of columns here is the same as the number of rows here. So we will get matrix C with dimension m by n. Okay, so what else can we get from this? Look, we can actually notice that matrix A is a collection of elements A, and look, what I'm going to do now is that instead of writing Aij, I'm going to just write Aik. Okay? And we need to somehow multiply this collection of elements by B, K, J. And as a result, we will get some collection of elements C, I, J. Okay, and maybe, knowing this, we can find the formula for element Cij. Because look, how will I be able to find element Cij? Okay, look, when we multiply matrices, we multiply every row from the first matrix by every row, by every column from the second matrix. And how do we do it? We multiply corresponding elements. So look, if I want to find element Cij, what do I need to multiply? Well, look. Okay, maybe this is going to be better explained. A. And look, when I'm using for example, first row of the first matrix when I multiply, when I move, I actually move across columns, right? This was the first column, then I move to the second column, then I move to the third column, then I move to the column N, right? Now, in case of matrix B, I do something a little bit different, look, right? Because here, what I'm actually doing is that I'm choosing a certain column, and then I'm moving along this column, but I'm moving in rows. So look, what is happening over here is that even though I'm choosing this row, I'm moving across columns. Over here, even though I'm choosing this column, I'm moving across rows. In this case, it should be Z here and Z. So now, look, if I multiply this by this, this by this, this by this, this by this. So, definitely, if I want to obtain element Cij, what should I do? I should sum up some elements. Okay. And which elements are those? Look, because if I want to take element that's going to be in this matrix. Okay. Let me give you an example. Okay, first, numerical example. So, I want to know I want to calculate element that is going to lie in the second row and third column of this matrix. So I want to know this element. How would I do it? Well, I would have to use the second column from matrix A. Second row from matrix A, and I would have to use third column from matrix B, right? So I'm looking for element 2, 3. Okay, so look, when I'm over here, I'm using elements from matrix A from the second column, right? And from this matrix, from the second row, and from this matrix, from the third column, right? So I get B3. And look, now, how do I move? I move along this Z makes perfect sense. So look, all I need to do is to write here k equal to 1 and Z over here. And look, if I want to, so basically if I want to find element 2, 3, all I need to do is to multiply the entire second row by third column. But remember, when I move across along the row, I use columns. This is why I use the second dimension here. And when I am in the third column and moving across the rows, this is why I have k here as a first dimension. And look, in more general, I can simply write the element Cij is equal to the sum A, I, here, and J. And look, with these symbols, with K, of course, equal to 1, 2, until Z, and of course I, 1, 2, until M, and J, 1, 2, until N. Okay, so look, what we've done over here gives us very clear indication on or how to multiply matrices from the practical point of view. So how to multiply one matrix by another, right? But also now we've examined how to derive the formula that will allow us to do it. And this is the formula that we needed. Okay, in the next video, we will take up the subject of vectors. Thank you for your attention and see you in the next video.